I'll start with the brief introduction of some observations of the risks. When we observe this, we often see they are quite structured. For example, in these tests, we see rings and gaps of different widths and gap depths. We can also see spar arms in some cases, very rare cases, unfortunately. And in some satellite observations, we can also see shadows in disks, and in some cases we see shadows and spars at the same time. And these structures are interesting because they give us an indication of what might be happening in the rings. For example, one explanation for the rings and gaps could be a massive planet, then that opens up a gap in this, creating the ring and gap structure. A possible explanation for large-scale spar arms is gravitational instability, whether this is massive enough of stuff gravity, this drives the evolution of the disk, where it becomes a stable and forms spar structures you see here. An explanation for the shadows is a misaligned inner disk that casts a shadow on the outer disk. And one of the types of this that will be the focus of this talk is a warp disk. So as defined here, the blue arrow you see on the bottom left shows the angular momentum vector of the disk in the highlighted region. And what you should see is that the direction of the angular momentum vector varies with the radial location of the disk. And that is what defines a disk when it's warped. In contrast, for a coplanar disk, you should see that the angular momentum vector is roughly a constant with a radial location. So, slide. One of the other things in this talk is what happens when there's a transfer of mass into the planet disk, and this is important because as I show later, stars don't evolve in isolation. They're influenced by the star forming environment. And when a disk is irradiated by the central star, the star is a constant source of energy. So the temperature structure of this will also be roughly constant in time. And I'll explain a little bit later why that's important. So, the other type of this that will be the main theme of this talk is the gravitational stable disk. And as I mentioned earlier, this is when the disk is quite massive. And the cumulative parameter is a useful quantity to understand when this is gravitational stable, and depends on the sound speed or currently the temperature of this, and the surface density or currently the mass of the disk. So a hot and low mass disk is stable, and a cold and massive disk is unstable. So that means how we model the disk thermodynamics is quite important. To mention that this for a particular mass of disk, if it's hot, it can be stable and look smooth, as you see here. But the same just mass, if it cools down enough, it will become unstable, forming spar structures you see here. So to calculate this thermodynamics in the simulation, we use the quantum energy force where Jonathan concludes we had alignment of the simulation, but it doesn't involve the energies between time steps. Instead, we use antiforce to start the photon throughout this to obtain the temperature structure of this. So, typically observational predictions of gravitational stabilities have been made using isolated disks that are unimpacted by the star-forming environment, because that makes experimentation quite a bit more straightforward. And one of the signatures of gravitational stabilities can be seen in kinematics, where if this was a smooth Kepler disk, these wings here would be but because these power arms are not moving at Keplerian speed, it causes these deviations in the channel map, which have been referred to as the GR wings. And here you can see that they are quite symmetric. When we look at observations of this that we think are gravitational stable, while we also see global deviations from Kepler velocity, they are less symmetric than what we expect for simulations. They're a bit more bent and asymmetric. Then that perhaps indicates something is missing from our simulations. And in recent years, we have started to understand that info is quite important in understanding what's happening in operations as we see that it's going to evolve in isolation. The star-forming environment is quite important, as you can see here with this moving in the isolated. And I saw earlier from George, info alone can also explain these power arms that you see in some observations. And additionally, in scattered light, in edge-on view of scattered light, we also see extended emissions, and the emissions from the top and bottom surface of this can also be laterally asymmetric, indicating that this is what potentially binary. So what I do in this work is I want to understand how misaligned info from the star-forming environment impacts a gravitational stability. And so to do that, we first set up a 0.15 masters and evolve it for 4 orbits in isolation until spark structures form. Then we add a 0.05 solar mass cloud that's initialized on a 0.3 falling parabolic orbit, similar to a flyby. And we incline the cloud. The cloud is inclined by about 135 degrees relative to this. So you can see the angular momentum vectors of the disk cloud and build system on the bottom right. And the reason we incline it is because it's now the inclining cloud is a source of angular momentum that's misaligned relative to this. So it has the potential to walk this. So in this video, we'll see what happens when the info interacts with a gravitational stable disk. You can choose your favorite view. The top left is based on view, where you can see what happens to spark structures. Bottom left is the edge-on view, where you can see how the disk becomes warped. And the view on the right is just a zoomed out view. So you can see the infall does affect the spar arms, but over time, the direction stability is still dominant in this case, and the disc has fragmented, forming forming a bound plumb. You can see in the bottom left, the spar arms are misaligned relative to disc. So essentially, we're forming in a warp and gravitational stable. Yes. We can also measure just how warped the disc is based on the tilt, twist, and the warp amplitude, which parameterize different components of the angular momentum vector in the disc. So in the top right, you can see the tilt, which shows how misaligned the disc, different part of the disc is. And you can see that at the location of plumb, the disc is only misaligned by a couple of degrees relative to other parts of this. But when we look at the twist, you can see that the inner part of the disc has this strong dependence on the twist based on its. The twist is strongly dependent on the radial location of the disc, indicating that differential precession happening in the disc. And when we look at the warp amplitude, it shows how steeply the warp is changing over the disc. And these small warp amplitudes show that it's a minor warp in the disc, and it's a continuous warp, so the disc is not going to break anytime soon. So we can also measure how gravitationally unstable the disc is based on the thermic field parameter I mentioned earlier. So the top panel shows the evolution of the surface density at 3 different snapshots, and the blue line is before the infalling cloud impacted the disc. The orange line is very soon after impact, where we can see there's an increase in mass where the cloud impacted this. And at 7.65 orbits, the current snapshot. In the simulation, you can see that a lot of mass has been redistributed inwards and informed transports. When we look at the temperature plots in the middle panel, we see that the informing cloud has warmed up the disk by quite a bit, which I'll explain later. And when we look at the asymmetry average to the cube profile, the increase in temperatures implies that the disk should be gravitationally stable, as the green line is above the dashed line, which is a large measure of when the disk is expected to be unstable. So it seems a bit opposite to what we showed earlier, where the disk is clearly unstable. So to explain why the disk is unstable, we look at the two-dimensional tuner cube to understand how gravitational instability is changing on a local scale. And the regions in red is where the disk is unstable. This is unstable. So you can see in this video, before infall, the spirals are symmetric and green. As infall impacts the disk above now, you can see the spirals are becoming asymmetric. And it's also a lot more messy over here, as you can see, infall impacting spiral arms, making the disk more gravitationally unstable in a local area. And I'll show that a bit more clearly in these three snapshots, which compare the three scenarios I mentioned earlier. At 5 orbits, it's a before infall. The spirals are clean, symmetric, nothing weird. Soon after infall, you can see in this region is where the infall impacted this. become a bit more stable in that local area. And after a period of continuous inflow, although the gravitational stability is a dominant again, you can see the spiral arms are a lot more messy, like especially here, because infall is falling onto the spiral arms, making them more unstable, and eventually causing them to undergo fragmentation. But infall also has a stabilizing influence on this due to the increased temperatures. So this is the same asymmetrically average temperature profile I showed earlier. It's using all the particles in simulations and includes PDB and shock heating. One of the possible reasons for the increase in temperature was the PDB and shock heating, but when that's turned off and the temperatures are recalculated, we see that it had a marginal influence on this temperatures. The other possible reason for the increased temperature is the presence of the infalling cloud itself. So I then separated the disk and cloud particles based on its azimuthal velocity. If the azimuthal velocity was roughly Keplerian, it was considered to be part of the disk, and if not, it was cloud. And on the left you can see what is considered disk, and on the right what is the cloud. You can see that the infalling cloud surrounds the entire disk. So in an isolated disk, the photons that propagate to the disk can eventually just escape into empty space. But because of this infalling cloud, it can absorb some of the stellar elevation and emit it back onto the disk, heating it up. And when we calculate the temperatures in the absence of the cloud, we see that this is much colder, which shows that the surrounding infalling cloud is reprocessing the stellar irradiation and heating up the disk. So one of the other ways we can identify a gravitational stable disk is based on the Fitch angle of the spiral arms. And in an isolated gravitational stable disk, the Fitch angles are symmetric and constant with a radial location, which when calculated for the disk before infall is exactly what we do. And after infall, when the pitch angles are calculated, both the pitch angles are still similar, but now they increase with a radial location, showing that infall can change how gravitational stability looks. In the next few slides, I will show how infall changes some of the other observational predictions of gravitational stability, starting with the scattered light observations. Before infall, the emission from the upper and bottom surface of this are quite symmetric. If you look left and right, the emission from top and bottom are pretty much the same, except for this bit here, which is the infalling cloud about the impact of this. However, after infall, we see that the emission is quite extended, and we also see a lateral asymmetry in between the upper and bottom surface. So if you look over here, like in this area, in the bottom, it's more bright than a similar area in the upper surface. Now, when we look at the continuum emission in phase one view before infall and parallel disk, the spiral arms are quite visible with high contrast between them and the inter-arm areas. After infall, the gravitational stable spiral arms have a lot lower contrast and harder to see because infall has shrunk the disk and increased the mass in that area. And both of those factors increase the optical depth of the disk, making it harder to see the spirals. In the edge-on view, with infall, very symmetric, very boring. And after infall, you can see that there's now quite a few or vertical asymmetries due to the mismatched spiral arms, and also you can see the falling gas falling onto this. Finally, we look at the kinematics, starting with the the, the channel maps. The left panel shows surface density just for comparison. The middle panels show the channel maps that were calculated using all the particles in simulation. And before info, you can see as expected from previous work, we see global deviations in these two wings as GR wiggle, and they're also quite symmetric. After infall, the infalling gas dominates the emission completely, and how to see what the disk is actually, what's happening to the disk. So we also calculate the channel maps using just the disk particles to get a better idea what's happening to the disk after infall. And you can see now the emission from the disk is not symmetric anymore. It's a bit bent, and the brightness in that window is also asymmetric. Sort of what like seen in observations as well. We can also look at the momentum map, which is the integrated emission of channel maps, and these are much cleaner than channel maps, where you can still see the spiral arms due to gravitational stability, but also you can see that it's much more messy after infall, where you can see all the influence surrounding gas impacting it. And then we look at the moment one map, which shows the velocity structure of the disk. Before infall, the two main things you can see are the spiral arms themselves, and also the red-blue split due to the rotation of the disk. After infall, you can still see the red-blue split, but it's a bit less clear. The other main feature is a bright red spot where the infalling cloud interacted with the disk, and the spiral arms are not visible anymore. So the main takeaway from this talk is that you can get climate formation in a warp disk via the combined influences of gravitational stability and misaligned infall. So it's a possible mechanism for forming misaligned planets. It's hard to say what happens to the planets as the disk continues to infall, as we can't follow this simulation after the disk has fragmented. And the impact of infall on gravitational instability is that it causes our arms to become more misaligned than the still initially had this, because the disk is quite a bit twisted. So in certain views, it looks more misaligned than other views. And infall can also take many of the asymmetric features when you edge on in satellite, showing that when we study young disks, that some of those features that could be warps could also be explained by, or could be due to infalling gas. And infall also makes it harder to see evidence of gravitational stability in the kinematics. So I'll leave it to that.
Yes.
Am I allowed to ask?
Yes, you are allowed. How much does your infall affect your M dot? Have you looked at the mass accretion rate? Does it correlate with the infalling?
I'm not looking at the accretion rate, but I looked at how this mass has changed. It's changed by about went from about 0.12 solar masses to 0.145 over about 4 outer orbits. So 0.15, 0.02 solar masses over 5,000 years. But in process, not talking this emission. If I could continue, there would be more gas.
The other comment from Anna's talk is it'd be interesting to measure like the disk stresses, like the alpha in your disk,
Yes.
with and without infall. It'd be interesting.
Yeah, I'm not gonna lie, but I mean,
But